All right, so here we're going a little deeper into two-dimensional shape review. We are heading into surface area volume. So in order to do shapes in 3 dimensions, we have to make sure that we have a strong command of all things 2-dimension first. All right, so first we're looking at an isosceles triangle. We want to find its area. So remember that any isosceles triangle, we can bisect the vertex angle. It bisects the base as well, makes it a 9 here and a 9 here. It divides our isosceles triangle into 2 congruent right triangles. In order to get to the area, I'm going to need the length of this segment right here. That is my height. So to get to my height, it is the leg of a right triangle. So my height ends up being the square root of the hypotenuse squared minus a leg squared. So 13 squared minus 9 squared is 169 minus 81. Square root of 88. So if I simplify that, that is 4 times 22. So I have a pair of 2's. My height ends up being 2 root 22. So now I build off of that. Area is half base times height. So half of 18 times 2 root 22. Well, half of 18 is 9. 9 times 2, we're back to 18. So 18 root 22 units are squared. Okay, next triangle is equilateral, but equilateral is still isosceles. So I can still divide it in half and make 2 right triangles. This one actually splits into more than just 2 right triangles. Each angle starts off as 60 degrees, so I can put 60-degree measures here and here. This 60-degree angle gets bisected, so there's a 30-degree measure here and here. So remember that your short leg is the x, your longer leg is the x root 3, and the hypotenuse is the 2x. So if my 2x side is 4, then my short leg is 2. I'd have a 2 over here as well. And then to get to that hypotenuse, or not my hypotenuse, my height right here, that ends up being 2 root 3. Let me say that back one more time. Short leg is x, that's 2. Longer leg is the x root 3, that's the height here, the 2 root 3. We were building off of the hypotenuse as 2x, that was 4. So now I can plug in. I know that my entire side here is 4. So area is half base times height. So half of 4 times 2 root 3. Half of 4 is 2. 2 times 2, we're back to 4. 4 root 3 units are squared. All right, next 2. Here we have to use our formulas for circumference and for area of circles. So first thing to note is that my diameter right here is 20. So my radius must then be 10. So if I want area first, area is pi r squared. My circumference is either pi times the diameter or 2 pi r, right? That makes sense since my diameter is 2 times r. So for area first, I'm looking at pi times 10 squared. So I get 100 pi. Units are squared. Always square units for area. And for circumference, I'm saying 2 times pi times 10 gets me back to 20 pi units. So that one was pretty basic. The next one is a little bit more complicated. All right, here I can tell that my radius is 6. And first I want to get to my area. So I can see that this is not a full circle, right? It's a portion of a circle. This measure here where it's a hollow little chunk, that's 90 degrees. So this portion here must be 270, right? I'm just taking 360 and subtracting 90. So this region here is 270. So the portion of the total circle that this part consists of must be the ratio of 270 to 360. And then we multiply that by the total area. The radius is just 6. So really, 270 to 360 is 3/4. I need 3/4 of the total area. The total area is 36 pi. So I like to visualize this as a fraction as well. And if I'm multiplying two fractions, I want to reduce top down or on the diagonals. So if I look at the 4 and the 36, they're both divisible by 4. 4 goes into itself once and into 36 9 times. So if I multiply 3 times 9, now I get 27 pi units squared. That is the area of my really 3/4 triangle, or not triangle, circle right here. So 3/4 of a circle right here. All right, if I want my circumference, what's goofy here is that this part is really 3/4 of the circumference. So I really need to get my total perimeter, because now I have these two segments, my two radii, that each have measures of 6. So here I'm going to write it as my total perimeter. Which is really 3/4 of my circumference, right? 2 pi r. My radius is 6. And then I have to add in these two slivers here. Each of those is a radius. So 2 radii. So I'm going to need 3/4 of 12 pi, right? 3/4 of the circumference, plus 2 radii. Each radius is 6. So again, if I'm going to reduce top down or on my diagonals, 4 goes into itself once and into 12 3 times. So this portion here is really 3/4 of the total circumference. So that ends up being 9 pi. And then I have to add the 6 right here and the 6 right here, which make up 12 total. All right, my answer here, 9 pi plus 12 units. Okay, next we're looking at area of regular polygons, and I'm focusing on the first 3 that have special right triangles embedded within. So I'm saying simplify any radicals. We should not need trigonometry for any of these 3. So the first one I'm saying, well, it's a regular polygon, so it must be equilateral triangle. So if I draw in the apothem right here, it creates a 30, 60, 90 triangle. Each of these angles starts at 60. So if I bisect this one, that's my 30. This is my 60 right here. Now my formula, area equals 1/2 apothem times perimeter. So I need my apothem, I need my perimeter. So opposite the 30, right here is my short leg. That's x, that's my apothem. My longer leg here, x√3. And my hypotenuse is the 2x. So my hypotenuse of the right triangle is the radius of the triangle, so of the equilateral triangle. So if that's 2x, then x must be 3. My apothem must be 3. My apothem connects the center to the side of any regular polygon. So then multiply that by √3. And I get 3√3 for this portion right here, the longer leg. So a whole side must then be 6√3. And I'm going to need the perimeter, so I multiply that by 3. My perimeter is 18√3. So plug these values in. We're going to take 1/2 of 3, that's the apothem, times 18√3. Now as I multiply, I'm going to take half of the even number. So half of 18 is 9. 9 times 3, and we're at 27. And then root 3 units are squared. Okay, the next one I'm looking at is my square, and the square has a lot of options. I can always do base times height or 1/2 AP, but in this case I see that I have a radius. So if I draw in another radius right there of 6, I actually know a full diagonal is 12. So I would choose to solve this one by going through the diagonals. Half of diagonal 1 times diagonal 2. So anytime that I have a quadrilateral where my diagonals are perpendicular, I can use this formula. So when I have perpendicular diagonals, that means my shape is a rhombus, a square, or a kite. I can use this formula. So if I plug in, I have half of 12 times 12. For a square, the two diagonals, they have to be the same. So half of 12, we're getting 6. 6 times 12, we're at 72. So 72 square units. Okay, last shape we have right here for this type is a regular hexagon. So here if I draw in the apothem again, right, that gives me a 30, 60, 90 triangle as well. I'm going to remind you of the formula. Area is 1/2 apothem times perimeter. So each of these angles starts off as 120. So if I bisect this one, that means I have a 60 here and a 30 here. So my short leg is the x. My longer leg is the x root 3. My hypotenuse is the 2x. And again, that's the radius of the regular hexagon. So that means that x must be 3, right? That's half of a side. A whole side must then be 6. And then the apothem is 3 root 3. Okay, that's the longer leg of the right triangle. It connects the center to a side for the regular hexagon. Okay, I know I'm going to need my perimeter. So if each side is 6 and I have 6 sides, my perimeter must be 36. All right, so when I plug in, I'm going to take half 3 root 3 times 36. So again, I'll take half of the 36, that's 18, times 3, and I get 54 root 3 units are squared. All right, next up, 2 more regular polygons, but these ones do not have that special right triangle embedded within them. So I'm telling you, we need to use trigonometry. Find each area, round to the nearest 10,000th. So I want 4 decimal spots. So here we have to remember SOHCAHTOA. Right? This is basic trigonometry. We use it anytime we have a right triangle. When we know one angle, one acute angle, and one side, I can solve for all of the missing parts. So looking over here, I know my formula. Maybe I start with that. I'm going to tuck that here. Area is 1/2 apothem times perimeter. So right now, I know that my apothem is 5. Okay, I can draw in this right triangle right here. But the issue is that I'm going to need an angle to build off of. So this angle right here is half of a central angle. That's what I like to build off of. Or I could do half of an interior angle right here. Let me do the 1/2 the central angle. So if I count up all of my sides, this is a regular octagon. I have 8 sides. N is 8. So if I want half of a central angle, I need to do half of 360 divided by 8. So half of 45 gets me a measure of 22.5 degrees. All right, so now I know that this measure right here, half of a central angle. Okay, I'm going to need the perimeter, so I'm going to solve for this leg right here, this side that's x. So to do that, from this angle, I have an opposite and an adjacent. So I'm going to use tangent. I'm looking at the TOA. So I can say that tangent 22.5 equals x over 5, my opposite over my adjacent. Visualize as a proportion and cross multiply. So x equals 5 times tangent 22.5. Okay, so if I type that in, 5 times tangent 22.5. So that gets me this measure right here. That is half of a side. That is x. X is about 2.0711. Right? I'm telling my calculator round the nearest 10,000th, 4 decimal spots. But I still need my perimeter. So I need to multiply that by 16 because this is half of a side. I have 16 half sides in an 8-sided shape. So I multiply that by 16 and my whole perimeter is 33.1371. I'm just going to make a note that I multiplied that by 16. All right, let me pull that away for a second and just plug that in right here. Okay, so if I multiply that across, I can say 0.5 times 5 times that previous answer. If I do it all with everything here previously in my calculator, I'm keeping it nice and precise. I'm not rounding to the very end. So my final answer for area is that it is about 82.8427 square units. All right, this next one is very similar. I'm just giving you a 5-sided figure. So the end value here is 5. My area formula is the same, so let's lay that out first. 1/2 apothem times perimeter. Okay. And if I draw in the apothem right here and then a radius like this, this is how I'm going to build my problem out. So if each side is 8, right here is 4, right? That's half of a side. Here's my apothem. I still need an angle, and I like half the central angle, so I'm going to find that one. So here I need half of 360 divided by 5. So half of 72 gets me 36 degrees. Okay, so building off of that angle, I have an opposite and an adjacent, so still using tangent. You can say that tangent 36 equals 4 over a. Build it out as a proportion, cross multiply. So a times tangent 36 equals 4. Divide out that tangent 36. Okay, so 4 divided by tangent 36, that is the apothem. So 4 divided by tangent 36. So the apothem is 5.5055. All right, so I have my apothem, 5.5055. Okay, in the perimeter, I have 5 sides. They're all 8, so that has to be 40. So if I multiply this across, I can say half the apothem, that's my previous answer, times the perimeter, that's 40, and that gets me my area. So my area is about 110.1106 units r squared. All right, let's flip it over to the next page. All right, this next page, I'm saying, well, now let's practice the more complicated trigonometry using law of sines or cosines. Find the missing angle or side measure. Again, round to the nearest 10,000th. And if the triangle is ambiguous, find both measures. So that only happens, good reminder, only happens when we have side-side angle, when we have the potential of the swinging door. So we use the law of sines when we have an angle with a side opposite. So right here, I have this angle with this side opposite. I need the angle that's opposite this side. And sometimes I have enough information to solve for it. So here I remember that if I know two angles, I actually know the third one because all of my angles have to add to 180. So my missing angle measure here has to be 66 degrees. So now I can use the law of sines because I do have an angle with the side opposite, an angle with the side opposite. So I can say that sine 70 is 2x, just as sine 66 is 215. So I've built my proportion and now I cross multiply. X times sine 66 equals 15 times sine 70. Then I just divide out the sine 66. All right, as I plug that in, I'm going to say that 15 times sine 70 divided by sine 66, just like that. So I get that my missing side has to be 15.4293. Okay. Next one, here I want this missing angle. I have a side opposite, I have an angle, I have a side opposite. And this is where I have side-side angle. So I know that I have the potential for the swinging door. If I do, this is where my hinge is. So I need to think, is this an ambiguous case or not? So if I look at the angle that I have, I see that the side opposite is smaller than the other given side. 8 is smaller than 12. So that means that this is ambiguous. This side right here, this door could swing into an alternate position right about here, making a very different looking triangle. My triangle could look like this as drawn, or it could look like this instead. That is entirely possible. So this triangle is ambiguous. There are two measures that work for theta. So if I solve for the first one, I start by saying sine theta is 212, just as sine 29 is 28. Cross multiply. So 8 times sine theta equals 12 times sine 29. Divide away the 8. Type it in. All right, so here I have 12 times sine 29, all divided by 8. So I know that sine theta is about 0.7272, and then I take the inverse of that ratio, and it's going to give me my first angle measure. So second sine, building off that previous answer, the first possible measure is 46.6534 degrees. So that's the angle that's right here. Remember that if that 8 swings to here, this triangle right here would be isosceles. So these two angles would have to both be 46.6534. So for my second option, the ambiguous case, we're solving for this angle right here, which is the supplement of the first. So I need to do 180 minus that measure, which gives me my second option of 133.3466. That is my other option for what this measure could be, what theta could be, because it's ambiguous. Again, it only happens with side-side angle. All right, the next two. So here in problem 12, I no longer have an angle with a known side opposite. So that tells me that I must be using the law of cosines instead. So a squared equals b squared plus c squared minus 2 times b times c times cosine a. You are either solving for an unknown side or an unknown angle. And here we're solving for the unknown side. So I start off with x squared equals, my other two sides are 8 and 9. So 8 squared plus 9 squared minus 2 times 8 times 9 times cosine 54. And the beauty of that is that I can type all of that in together. So I can say 8 squared plus 9 squared minus 2 times 8 times 9 times cosine 54. Enter. So it tells me that x squared is about 60.3589. So the last thing that I need to do is take the square root of each side. And I know algebraically I get a plus or minus in my answer, but it is a measure, has to be the positive. So square root of that previous answer, and we get 7.7691. Okay, next one, I'm still using the law of cosines, but in this one I'm given all three sides. I want this angle. So I need to think, what is that angle opposite? It's opposite the 7 right here. So in my formula, I start with the 7 squared, right? Again, it's the angle that's opposite here, this side. So I start with the 7. So 7 squared equals the other two sides. So 8 squared plus 10 squared, right? The order of those does not matter. It's just that the 7 goes first. Okay, minus 2 times 8 times 10 times cosine theta. Now for this one, I have to be really careful with my order of operations. I need that cosine part right here all by itself. So let me clean this up. I have 49 equals 64 plus 100, okay, minus 160 times cosine theta. Okay, if I keep going, now I have 49 equals 164 minus 160 times cosine theta. Now here's the thing, this is a product. This is being multiplied. I cannot combine that 164 minus 160 because the 160 is attached to the cosine theta. So I need to get this part all by itself. So I need to next subtract that 164. So I get negative 115 equals negative 160 times cosine theta. Okay, now I need the cosine theta by itself, so I can divide each side by 160, by negative 160. So here if I'm looking at negative 115 divided by negative 160, I now have that cosine theta is about 0.7188. And since I want the angle measure, now I use the inverse of cosine with that ratio, and it's going to give me the angle measure. So inverse of cosine, second cosine, build off that previous answer, and we get 44.0486 degrees. All right, last skill, we're looking at a variety of different quadrilaterals. So we just have to identify each one and then find all the missing parts that we need. So the first one right here is a parallelogram. I can see that my opposite sides are parallel, so it's just a parallelogram. And I know that my area is base times height. So I can picture this right triangle, for example, right here. If I cut that out, I could slide it into this position right here, and it would make a solid rectangle. So area is base times height. So here my base is 11. I can see that, but I don't know my height. My height is this perpendicular segment that connects those two bases. But if I look at what I have marked, I have a 13 right here. I must have a 13 here. So I can see that this triangle right here, this right triangle, is a common triple, right? It's a 5, 12, 13. So my height must be 12. So 11 is my base. My height is 12. That makes 132 square units. Okay, next I see another square, but this time I'm giving you the apothem. So here I'd probably just draw in another apothem, make that 2 root 5. So each side must then be 4 root 5. My base and my height must be 4 root 5. So I would just do base times height here. So 4 root 5 times 4 root 5. Okay, so base and height both 4 root 5. 4 root 5 times 4 root 5 is like saying 4 times 4 times 5. So we get 80 square units. Okay, next one here is a rectangle, but the issue is that I am giving you a base but not the height. So I need to think about how to build off this right triangle that I see right here. There's no common triple with a 10 and a 26, but if I divide each of those by 2, this becomes 5, this becomes 13, so this would be 12, but 12 then times 2, so must be 24. So this is really the same triple that we saw earlier, the 5, 12, 13, but times 2. 10, 24, 26, and it was the 24 that we needed. So base here is 10, height here is 24. Base times height. So 10 times 24, and we get 240 square units. All right, we're getting close. Okay, next one here, I see that all of my sides are the same. So this is a rhombus. So my first thought is, why am I building off that 12? Well, I can see that this is a 30, 60, 90 triangle. So my short leg is x, my longer leg is x root 3, the hypotenuse is 2x. So here that longer leg is 12, that's the x root 3. If I take a third of it times root 3, that tells me that my short leg is 4 root 3. And then the hypotenuse would be 8 root 3. Okay, so if I build off of that, right now here I could say that this part is my height, the perpendicular segment that connects my two bases. So right there is my height. So I would need to make this part then here my base. So if I see that each side is 8 root 3, I can say, well, this side also 8 root 3. So if I solve it this way, I could say base times height, 8 root 3 times 12 will get me 96 root 3 units squared. Okay, you might also see that you could also go through the diagonals, because the diagonals are perpendicular, and we know that for any rhombus, the opposite angles are congruent and bisected. So together, this must make up 120, and if it's bisected, this must be 60 and 60 here, and then also here, which means that these other angles must be 30 degrees. I'm just showing you another way of solving. And this method is going through the diagonals, half of diagonal 1 times diagonal 2. So if I go this route, right, if this is 8 root 3, then this right here is 4 root 3. And then here, let's see, this would be 4 root 3 times root 3. I would get a 12 here. That would also be 12, and then that would also be 4 root 3. So if I take half of the short diagonal, 8 root 3, and then the longer diagonal, 24, Half of 8 is 4. 4 times 24, we're back to 96 root 3 units squared. So again, just an alternate way of getting to the same conclusion. All right, we got 2 more. So here I see it's an isosceles trapezoid. Here are my 2 bases. So if I think of my area first, it's the average of the 2 bases, half of base 1 plus base 2, and then times the height. So average of the bases times the height. So my bases, I know those. I have 14, I have 30, but I do not know my height. Now when it's an isosceles trapezoid, if I draw in these 2 perpendicular segments, I really have 2 congruent right triangles here and here. So that 14 first slides down right here. And then if I think about what's left then, 30 minus 14, I have 16 units that I need to split equally. So here I have 8 and here I have 8. So here I see another common triple. We see them all the time. It's my 8, 15, 17. And right here must be the 15. That is my height. So now as I multiply across, right, I'm going to say 1/2 times 44 and then times 15. So 330 units r squared. All right, one last one. So here is my kite. And for any kite, we have perpendicular diagonals. So that means I must be going through half diagonal 1 times diagonal 2. Now I could also just find the area of each triangle and add them up. That's another workaround. So here again, I see another common triple, a 20, 21, 29. So this right here is 21, okay, which means that this is also 21, right? If I look at this shape right here, that's really an isosceles triangle right here where I'm bisecting that vertex angle and that base. So I have a 21 here and a 21 here, okay, and then, or not 21, 20. I'm putting the wrong number. That's the 20 because it's the 20, 21, 29. So if that's the 21, that's the 20. All right, so let me say that back. That's a 20, that's a 20 because it's a 20, 21, 29. Again, isosceles triangle, that base got bisected. All right, so now looking at the 45, 45, 90, the 2 legs have to be the same. So if this is 20, this is 20, this would be 20 root 2, right? I don't need it, but I'm just filling it in because I know it. So now the first diagonal, the short one here, 20 plus 20 is 40. So I put a 40 in here. My longer diagonal is just a smidge bigger. That is 41. So now if I multiply across, I'm taking half of 40. That's 20. 20 times 41, and I'm at 820. Units r squared. All right, I think I've covered all things 2D. Have a good day.